Hello everyone. Today we're gonna learn about graph data structure. This is the 10th and the last data structure that we're gonna cover in this series. Graph data structure is used to record relationships between objects. Graph combined with the 9 data structure we have learned so far gives us the capability to model anything in the world and the relationships between them. This tutorial is a part of the data structures and algorithm class. To save me some time, I have selected a video that presents the fundamental knowledge about graph, such as what is a graph, what is a node in a graph, what is an edge, and so on. This video also has some cool animation about graph that helps you to understand the fundamentals better. If you are totally new to graph, I strongly suggest that you pause the current video and watch this one first. If you already know the fundamental about graph, you can skip this video and continue watching the current one. Either way, I'm gonna give you 5 seconds to pause this video. Okay, now you know the fundamentals about graph. Let's take a step back and understand why we need graph. Graph is a data structure used to model relationships, and it can be used to model any kind of relationships. So tree is basically a symbol graph. You can understand the reason why we need graph data structure by looking at this photo right here. This is a presentation of H2O molecule, which we commonly known in daily life as water. And this presentation is a graph. By looking at this, you can see that at the smallest and fundamental level, like atoms and molecules, things has relationships between each others. And this holds true in our world, that anything has relationship to something. That's why graph is a very popular data structure. And it's also one of the most frequently asked data structure in coding interview problems. So now you know what graph does and why it's an interesting subject in programming. Next, we're gonna learn 2 important skills on graph data structure. The first one is to present a graph into code. So we're gonna take in any visual presentation of graph and turn it into code where the information can be stored and processed by the computer. And the second skill we're gonna learn is to draw a visual graph from code. That means if anyone gives you a graph data, you're gonna be able to use that data to draw a visual presentation of that graph. There are many ways to present graph into code, but in this tutorial we only learn about 2 ways to present graph into code. The first one is Adjacency List, and the second one is Adjacency Matrix. If you can understand and use these 2 ways fluently, you'll be able to quickly understand other ways of graph presentations, or translating one presentation to another. Because the visual presentation of the graph, with one specific presentation in the code, is a one-to-one mapping. Next, let's learn how to present a directed unweighted graph into code and vice versa. In this example we have here in the picture, we have a visual presentation of a graph that models the relationship between airports. The nodes of the graph, also known as vertices, are the airports. The 3 letters we see here are the international short code of the airport name. For example, SFO is San Francisco International Airport, and these airports are close to big cities. For example, SFO is close to San Francisco, ORD is close to Chicago, and so on. The directed arrow is presenting that there is a flight from one airport to another. For example, we can fly from San Francisco to Chicago, or from San Francisco to Denver. We can also fly from Chicago to San Francisco, but there is no option to fly from Denver to San Francisco. Together, the nodes and the directed arrows give us the information about where we can fly to if we are at a particular airport. For example, if I'm in JFK, I can fly to Denver and I can fly to Houston. I can also fly from New York to San Francisco if I take 3 flights. The first one from New York to Denver, the second one's from Denver to Chicago, and the third one is from Chicago to San Francisco. So that's how a visual presentation of a graph gives us the information, and how we as humans use the information to navigate around, or to see what options do we have. Next, we're gonna learn how to present this graph into code using Adjacency List. Adjacent means next to. Adjacency List is the list of immediate neighbors. As you can see, this graph started with an array, and each index of this array represents an airport. For example, index 0 represents SFO, as you can also see here in the visual presentation. And ORD had index 1, Denver has index of 2, JFK has index of 3, and IAH has index of 4. So basically, if you start to create a graph from scratch, what you do is you're gonna choose an index for all of the airports. What airport goes with which index is totally up to you. And you put the name and the index of the airport in this empty array, like this one. And initially, this array here representing SFO is gonna be empty. The next step is simple. You're gonna find out the immediate neighbors of the current node and put them into the array of that node. So at index 1 SFO, when we look at the graph, we see that SFO can go to ORD, index 1, and DEN, index 2. So we take 1 and 2, and we put them to SFO array. And if we add ORD, index 1, we can see that ORD can go to SFO, index 0, and JFK, index 3. Then we're gonna put 0 and 3 into ORD array. And we will keep repeating this step for the rest of the nodes in the graph. When we finished, we have presented this visual graph into code with adjacency list, the list of immediate neighbors. An important note to know here is that if you change the index of these airports, the code presentation of the graph will look differently. But if you keep the index like this and give this graph to 2 different students and tell them to use adjacency list to present this graph, the result of the 2 students must be the same. And they must be the same with this graph we have right here. So when the index convention is fixed, the visual presentation and the code presentation of a graph is a one-to-one mapping. So the mapping from airports and indexes as we see here is important, and it must be kept, either in a comment like this or in some sort of mapping in the code. Okay, we have seen how to navigate around the airports with the visual presentation of the graph. Now I will cover the visual presentation of the graph and see how we're gonna navigate around the graph using the code presentation, the adjacency list. Okay, so the first question is, if I am at JFK, where can I go? To answer that question, we know that JFK is index 3, and we are here. We look at the neighbors of JFK, which is 2 and 4. So we know that if we are at JFK, we can go to 2, which is Denver, and 4, which is IAH. And that should be the same answer if we look at the visual presentation of the graph. So if we are at JFK, we can go to 2, Denver, and we can go to IAH, Houston. That's the same answer we have from the code. Now the second question is, can we go to SFO from JFK? By looking at JFK neighbors, we don't see SFO in here. So we know that we cannot go directly from JFK to SFO. But what we can do is we can go to JFK neighbors and see if we can go to SFO from there. So we start at index 3. We can go to 2, which is Denver. And from Denver, we can go to 1, which is Chicago or ORD. And from ORD, we can go to 0, which is SFO, the destination that we want. So the answer is yes. We can go from JFK to SFO. And if we look at the visual presentation of the graph, we start at JFK, we can go to Denver, we can go to Chicago, and then we can go to SFO, which is the same answer we have from the code presentation of the graph. And that's how we navigate around the graph using both visual and code presentation of the graph. It's important to know how to navigate around the graph in both ways, because the visual presentation is how we as humans intuitively solve the problem. And then we're gonna use the code presentation of the graph to program the computer our solution. To draw a visual presentation of the graph from the code is fairly simple and straightforward. First, we draw all the nodes with the name and indexes. In this example, we have 5 nodes. We're gonna draw the nodes first and put the name at the index to the node. Then we simply make the connections between the nodes by drawing arrows from the current node to the nodes in its list. For example, we're gonna have 2 arrows from node SFO index 0 to node 1 and 2, which are ORD and DEN. So we're gonna draw an arrow from 0 to 1 and 0 to 2. We keep repeating this step until we finish the whole graph. Next, we're gonna see how to use an adjacency matrix to represent the relationship with this graph. Adjacent means right next to. Adjacency matrix is a square matrix that will record the immediate neighbors of the current node, and the matrix looks like this. To present this visual graph into the adjacency matrix, We start with an empty array, and just like the adjacency list, we're gonna have empty arrays representing each airport with the airport short name and its index. For example, SFO is 0, ORD is 1, and so on. Each of the columns in this matrix also present the exact same airport with the exact same index. You can see the sequence of the airports here in the column, in the same sequence of the airport in the rows. Then we initially fill the matrix with zeros. After that, we look at the visual graph, and we can see that SFO can go to ORD and DEN, which is 1 and 2. So we come over here and replace the zeros, presenting ORD and DEN, into 1s. This number 1 right here is saying that SFO can go to ORD and SFO can go to DEN. The rest of the zeros says that SFO cannot go to JFK, SFO cannot go to IAH, and SFO cannot go to itself. Then we can repeat this step for the rest of the airports. When we finish, we have the adjacency matrix, which presents the relationship between the airports, just exactly like this visual graph. Now let's see how we navigate around the graph using this adjacency matrix. Just like before, we're going to be interested to see if we can go from JFK to SFO. So we start at JFK. By this list of neighbor of JFK, we know that JFK can go to DEN and JFK can go to IAH. And the index of DEN is 2. So we look at DEN at 2, and we know that EN can go to ORD because it has number 1 here. And we know the index of ORD is 1. And by looking at the neighbors of ORD, we know that ORD can go to SFO because it has a 1 here in this column. So to answer our initial question, the answer is yes, that we can go JFK to SFO. And that's exactly what we can see visually from this graph. JFK go to DEN and go to ORD and then go to SFO. And that's also the exact way that we have from graph number 1 with adjacency list. Next, to construct this visual representation of the graph here, from the adjacency matrix, we're going to start with drawing out all the nodes in the graph. We have 5 nodes here, and we're going to label them with their names and indexes. For example, SFO and 0. And then we look at the list of the immediate neighbors. For example, in immediate neighbors of SFO is ORD and DEN. Then we know that SFO have the direct connection to ORD and DEN. So we're going to draw an arrow from SFO to ORD, like the one that we see here. And we're going to draw another arrow from SFO to DEN, like this arrow here. We can repeat this step until we finish all the nodes. And after that, we're going to have the visual presentation of the graph. It should be exactly the same with this graph, and also the same with the visual presentation of this adjacency list. Once the naming and the indexes are fixed, it's a one-to-one mapping from visual presentation and code presentation. Now there's an important note that we should know here. Because this is a matrix, and we use the row of the matrix to show the list of immediate neighbors in this example. That's why we have from row to column here, from this row to the column. But because this is an n by n matrix, a square matrix, we can actually use the column to contain the immediate neighbors of a node. And if that case happens, the relationship is going to be from column to row, which is the opposite of what we're having here. So the point is, documentation is very important. If we stripped out all the comments of this matrix can be anything, or it can be nothing really. So you should know that the meaning that we put here in this mapping and convention of directions is as important as constructing the graph. In real-life application, the matrix and the graph will be way more complex than this. So capturing the meaning behind the matrix is even more important. Anyone that tells you that documentation is not important is just a sloppy coder who doesn't care about the future of the code base and his or her co-workers. So when you join a team or a company, always try to make decent documentation to avoid any confusions or errors. So by now we have learned how to present a directed, unweighted graph into code and vice versa. And by learning how to navigate around the graph in some degree, we also answer the most important problem in graph. That is there a possible path from one node to another? We're going to learn more about problems like this in detail later. There's a note to choose to use either adjacency matrix or adjacency list to present your graph. That is, the list is dense and the matrix is sparse. If we look at our matrix right here, we see that there's a lot of zeros, and these zeros take a lot of space. Imagine you have a graph of 1,000 nodes, and each node only have like 3 to 5 connection with other nodes. Then the adjacency matrix represents that graph. We have 90% of its elements as zeros, and that's not very efficient. That's why we call matrix is sparse. And if we look at the adjacency list here, we see no zeros. We can see that all the elements in the list is the minimum requirement to represent this graph. That's why we call the list is dense. Choosing either list or matrix to represent the graph depends on what kind of application you want to develop. But the key takeaway point here is, both of them can do the work. The adjacency list is gonna save a lot of space compared with the adjacency matrix. Next, we're gonna learn how to present the directed weighted graph into code and vice versa. A weighted graph is the graph where the edges are associated with a number, representing the weight. This weight can mean anything. For example, the number 2 here can be the cost of the flight from SFO to ORD. And from ORD back to SFO is gonna cost 4. Or the weight here can present the time to fly from one airport to another. For example, if we fly from SFO to DEN, it's gonna cost 10. And from DEN to ORD, it's gonna cost 6 units of time, maybe in hours or minute. The unit is actually up to us. To present this additional weight information for adjacency list, instead of using just a single number presenting the index in the neighbor list, we're gonna use a pair of numbers. The first number is indexed, and the second number is the weight. So SFO can go to index 1, which is ORD, with a cost of 2. And SFO can go to index 2, which is DEN, with a cost of 10. And that's what we see over here. For adjacency matrix, to represent the weight, we simply replace the number 1 with the number of the weight. So for example, with JFK here, we can go to DEN with the weight of 4. And JFK also can go to IAH with the weight of 3, which is what we see here. So that's how we present a weighted graph in adjacency list and adjacency matrix. With this additional information of the weight, our graph now looks more realistic than ever. And we can actually use it to represent some problem in real life, such as finding all possible routes from SFO to JFK, and find the cheapest flight from SFO to JFK, where the weight represents the cost of the flight. Or another problem is find the shortest flight from SFO to JFK, where the weight represents the time to travel from one airport to another. Next, we're gonna learn about undirected, unweighted graph, and learn how to translate visual graph into code and vice versa. This is fairly simple. When we say undirected graph, that means the graph is always bidirectional. We can always go from a node that it's connected to and vice versa. So instead of drawing 2 arrows back and forth, we can just simply draw a bar. Unweighted means these connections are equal. So to translate this graph into code, we can simply apply what we already learned to do this translation. For example, for the adjacency list presentation, we will start with SFO, which has the index 0, and then we're gonna list all the nodes connected to SFO, which is ORD 1 and DEN 2. Next, for ORD with index 1, we're gonna list all the nodes connected to ORD, which is SFO 0, DEN 2, and JFK 3. And we can keep going for all the remaining nodes. To present this graph with adjacency matrix, we simply start with the n by n matrix at the beginning, filled with zeros, where n is the number of the total of the nodes. And then we're gonna replace the 0 with the connections. Remember, our matrix is from row to column. So from SFO index 0 to all the airports in the columns. So for SFO 0, it's connected to ORD 1 and DEN 2. So we're gonna mark SFO row, column ORD and DEN 1. Next, ORD index 1 is connected to SFO 0, DEN 2, and JFK 3. So in ORD row 1, we're gonna mark 1 as column SFO, column DEN, and JFK. And we keep doing that for the remaining nodes to create the adjacency matrix representation of this graph. Next, we're gonna learn about undirected, weighted graph and how to present the visual graph to code and vice versa. This is fairly simple. With all the knowledge that you learned so far in this tutorial, you can actually do this by yourself. Now remember, undirected means always bidirectional, so two connected nodes can always go back and forth. And because it's weighted, these edges now has a number attached to it. So to present this additional information in the adjacency list, you're gonna use a pair of two numbers. First one is the index, like we had before, and the second one is the weight. So if we see 1, 2, that means the index 1 and the weight is 2. Let's start with SFO index 0. It's connected to ORD with index 1 and the weight is 2. So in SFO list index 0, we have 1, which is ORD, and 2 is the weight. This weight from SFO to ORD can present anything. For example, it can be the cost in US dollars to buy a flight ticket from SFO to ORD, or it can be the time it takes to travel from SFO to ORD. It can mean anything really. It all depends on our notation, depend on what we want. Next, SFO is also connected to DEN index 2 with the weight of 10. So in this list we see 2, index of DEN, and 10, the weight of the connection. Then we're gonna keep repeating this step for the remaining nodes to create our adjacency list presentation of this graph. For adjacency matrix, it's even simpler. We can just take the unweighted graph we had before and replace the ones with the number of the weights. For example, for SFO row, we have 2 at ORD column and 10 at DEN. And that's what we have here. And we keep repeating this step for the rest of the nodes. Then we have the adjacency matrix representation of this graph. Next, let's talk about graph popular problems and algorithms. There is a lot of problems related to graphs, but the majority of them will fall into these two categories. The first category is we want to visit the nodes in a particular order. This has the same meaning of collecting the node data in a particular order. For example, what are the options to go from SFO to IAH? And based on our graph, one option can be SFO to ORD to JFK and to IAH. Another problem on a social network is, do Jack and Jill have shared friends? The second category is, how can we modify the graph to satisfy some conditions? One example can be, if we have two cities connected by bridges, what are the minimum of the bridges should be removed to isolate them? To solve these kind of problems, human has been conducting extensive researches on graph algorithms, and there's a lot of graph algorithms, and we will discuss in details for some of the most frequently used algorithms in coming dedicated tutorials. But the key takeaway from today is really how to present the graph into code and vice versa, and how you can navigate from node to node in the graph by looking at the code presentation of the graph. If you can do these two things and want to feel challenged, try solving the airport problems that we mentioned above. You actually have learned 2 algorithms to solve this problem in 3 tutorials, which are depth first search and breadth first search. That's it for today's tutorial. Thank you for watching, and I will see you in the next video.